Okay, so we're going to look at modeling with linear functions. So some linear modeling for this question. So we're told that in a chemistry experiment, a liquid is heated up and the temperature is recorded at different times. Some results are shown in the table. We need to plot a graph of this data on our calculators. Take your calculator in your hand at this point. You need to have your calculator in your hand. You need to bring your calculator to class. Okay, does anyone remember how we might do this? How can we plot this? Guys?
You go on a new document, and then you put this in spreadsheets.
Yes. So here in our new document, we press Control and add a page. You see here above document, it says add a page. And we're going to add a list in a spreadsheet. Guys, continue.
And then you can name one of the lists X and the other Y.
So when you name it, make sure you name it up here at the top, not the row below, because that's where you put the formulas in. We don't want it there.
And then you plug in the data.
We insert our data, 6, 8, 10, and then 130, 209.8, 210.3. Notice that I'm typing in 4 significant figures, and my calculator is set to display only 3, but it will still hold 4. 369.2. Okay. So far we have our data entered. So what we're going to do next is we want to plot it. So the purpose of the plotting is to see what shape it's got. So the purpose of this next stage is to see the shape. So we're going to press Control, add another page, and we're going to choose number 5, add data and statistics. We see the points laid out here. If we click on the x-axis, we can assign the x variables to that axis. If we click here, we can assign the y variables here. And what's important about this picture is the dots appear to be in a straight line. The dots appear to be in a straight line. If they're not, if they're in some kind of a curve, we're going to choose a different model. So the purpose of doing the scatter plot on our calculator is to make us choose an appropriate model. So in B, we have to choose the appropriate model. Which model would we use?
What do they mean by model?
So what they mean by model is you can use a few different types. In this case, we're going to use y is equal to ax plus b, or y is equal to mx plus c. We're using this model. This is a linear model, and the reason we're using this one is those dots look like they're in a straight line. If they're in a curve, you might use a quadratic model or an exponential model and explain why you're doing that. But in this particular case, our justification is the dots appear to be in a straight line. I will use a straight line model, or a linear model as we call it. So we need to determine a reasonable range, domain and range for the model. So
for the domain, it's 4 and 10.
So for the domain, we have a little bit of space.
Do I have to write each one?
So for the domain, we are going to have x is defined over a period of 4 up to and including 10. So this is our domain. This is our domain. We go from smallest to largest, and this is what's acceptable. We don't know what the rest of the model might look like. So at the moment in this, we've got a few points that look like this. And it's reasonable in this domain to assume it's a straight line, because it appears to be in a straight line. But that isn't necessarily the case. A common question I might do would be to get students to measure their height and their shoe size and their foot size. If you measure students' height and their foot size, they correlate. And students of your age would correlate and look something like this. But if you extrapolate that beyond the domain and you continue it, when you get down, you end up with something like this, where you basically have a baby, and they're about 30, 40 centimeters tall, but they have no feet. And if you actually take adult data and extrapolate it down, you end up with that kind of a result. So that's why we have a specific domain. It works really well for adults, but what you find is the model is going to have a different shape for infants, particularly in the fetus stage. It's going to have a very different sort of shape, and the model might have different shapes in different intervals for different reasons. That's why when we have this type of modeling question, we have to say that this is only valid within the data that we know about, not valid for the data we don't know about. What would the range be? Well, the range is just going to be the range of possible y values. We have to look through the data from the smallest to largest, and our range is going to be y. It's going from 130 up to 369.2. Okay, D, find the equation for the model. So to find our equation, we want to do a regression analysis.
So I found another way to do it.
There's a couple of ways to do it.
I did it on the one with the spreadsheet.
There's 3 different ways to do it. I'd like to show you my preferred choice. They're all basically the same, so we can do it here, and I don't usually recommend doing it here. We can just analyze it and find a regression using a linear regression. And we get the straight line, and there's the equation. That's the equation. You can do this to find the model. If we're going to use the model a little bit more, I prefer to do it here. So I'd like to show the steps for this one. I'd like to show the steps. If you're ready, follow me along. We're going to press menu. We're going to use statistics. We're going to use stack calculations, and then regression. So menu 613. It pulls up this dialog box, and we can choose the X list, the Y list, and then saving it to F1. We click OK on that. There's our model. So for D, we get Y is equal to, and we've got 39.9 as our gradient coefficient.
We did this one too.
We did,
And 9.
which is why Kais remembers it.
So you told me about it.
I remember. Good times, good times. Comment on your model. What sort of comment should we say about our model? Linear model. It's a lovely model. It's written in blue. So we've got a linear model which is valid for this domain. You can see it's not going to be valid outside this domain.
Didn't you say that the X and the Y have word correlation?
What it would mean if we were to extrapolate using this model is the water started off at minus 30 degrees, which seems a bit odd. Why would the water be at minus 30 degrees? That it freezes at 0. Can you see how the model isn't going to work? When the time is 0, we're going to get minus 29.5 as our answer. So that's not really going to make sense because water can't be that temperature. It's not water anymore, it would freeze.
Would it ask us questions like that?
Yes. What is this course called? What's the second word? They ask that question a lot, and it's usually the harder questions on the paper. Okay, so use your model to estimate. So estimate the temperature of the water 4.5 minutes after the experiment had started. So we're just going on to EI. So press the variable button here, choose your model, which was F1, and we can enter in the value 4.5 and press enter. We will get 100. So y of 4.5 is equal to 150. And that would be degrees centigrade. quiet, it's not water.
So what you press to get the F1 equals 5? You press variable
Yeah, so we press variable here,
and F1.
and then F1, which is where we stored it, and then we type in our numbers. The water, find the temperature of the water 20 minutes after the repair started. 20. 769. Okay, now I can see where I'm getting confused. Here in the question, it's talking about a liquid being heated. And then here in these questions, it's talking about water. Which is what I'm like looking at this, and there's, because obviously this makes no sense. Water doesn't become 769 degrees. Other liquids can, oils can. You can get an oil up to that kind of a temperature. Yeah, sure. We only have a really short lecture to go through today, but sure, we can go during it.
He's telling me don't go. Sit down.
Oh, basically.
Wait, so what?
Thanks for interpreting from British to regular English.
Articulating on your
He's a very clever chap.
Yeah, thank you, mate.
So the point of this is to show that this is not a realistic
Yes,
experiment?
yes. So the model wouldn't really be working outside of the domain. So if we look at our domain is from 4 to 10. We get reasonable results within that. But when we go outside of that, we end up, it's just going to keep getting hotter and hotter. And that's not going to happen for any liquid. Any liquid would have a stopping point. It would turn into a gas.
So our answer would have to be like scientific, right?
Yes, yes.
This is not
Because you can't just leave it like that.
No. So for G, comment on your predictions. You can see clearly why it's so dangerous to extrapolate the data. We need to learn this word. Have you come across the word extrapolate and interpolate?
Yes, sir. Very long time ago.
Yeah. Just to remind those of you. So our data looks like this. So our model is valid in that region like this. It is unsafe to extrapolate the data beyond the two end points because we end up with a value over here at 20, what was it, 700. What did we get? We got 769. Here we have 20,769. This is an unsafe prediction. This is an unsafe. I'm going to use very specific words here. Very specific words. So the typical comment would be, it is, and I'll do the keywords in English, in green. It is unsafe.
Would that word only be used for if we get something to do with an experiment?
No, anything to do with extrapolation. So with statistics, often in statistics, we use the idea of things being unsafe to use or misuse statistics. So this is a statistic method that we get our model with. If we were to use this incorrectly, try to stay focused. We would talk about it being unsafe to extrapolate data in this
Well,
way.
if we did the thing with like, I don't know if this would apply to this, but the one where you said about the feet and the height.
Yeah.
And that would.
It would be unsafe to make such a prediction.
Okay.
It is unsafe to make predictions outside the domain of the model. This is extrapolation. Let me explain this word extrapolation. So what we do is we are basically saying that these two endpoints are the two poles. These endpoints are the poles. The two endpoints mark where the data is safe and where it is not safe. They're the poles at the end marking the area that we can use. So
interpolation is when it's inside within those borders, like within the maximum.
Interpolation means between the poles.
And extrapolation is when it's outside.
Outside of the poles. Extra means outside. So for instance, we talk about extraterrestrial. An extraterrestrial is something that comes from outside of our Earth. Terra is Earth. Extraterrestrial is a being which doesn't come from this Earth. So here at these sides, this is extrapolation. And here in the between is interpolation.
So it's okay to make predictions inside, but it's not okay to make them.
Exactly. It's unsafe to make it outside. Okay. As long as you have a good line of fit. So there is another reason it could be unsafe, and that's because your line of fit is not a good fit. We've talked about the goodness of fit before in previous courses. The R value.
I remember that one.
You remember that value?
Yeah.
We'll come back to it when we look at. If you see here, look at the R value.
Perfect.
It's perfect, so it's very, very safe. So as long as this is over 0.5, it's safe to make.
What if it was 0.5? Could you say
It's safer to predict when it's over 0.75 or the absolute value is over 0.75. It's very unsafe if the absolute value is below 0.25. It's in between.
So I would write it in between safe and unsafe. It's over 0.5.
Yeah. Okay, that's it for today.